A few quick words about SEG Evolve for those of you who aren't familiar with it. So SEG Evolve, as you see from the slides, it's a 6-month part-time virtual internship for students. It's collaborative, global, and inclusive, and we focus on the future. And the most important thing is we teach the skills necessary to be successful in multidisciplinary, real-world, digital E&P settings. And maybe the most critical part is that it includes extensive mentoring by highly experienced industry experts like Mr. Forrest. Just a couple of quick things. In Evolve students, you learn how to make maps such as these, but we really emphasize a lot the importance of the geologic thinking, which is this slide here. You'll see this again in Mr. Forrest's presentation. Another very key element, which is very closely linked to what I just said, is we like to have the philosophy, if you understand it, you should be able to draw it. And if you can't draw it, you probably don't understand it. So we often emphasize the ability to draw what you're thinking geologically. Evolve is supported by a series of companies, and we've had teams from all over the world. Looking forward to adding more. And for those of you who are currently early career professionals, wish you had done this, I'm pleased to tell you that we have Evolve Professional, which is basically the same thing as Evolve for the students, except we do it in your company, customized for your own staff. Anyway, if you want more information, go to one of these sources. So I'm going to stop sharing, introduce Mr. Forrest. Long distinguished career, worked at Shell for many years, then he worked on his second career at Maxis YPF. Then he worked on his third career, which is he established the DHI consortium, and that had over 30 companies participating. And now he's on his fourth career, which is working with me in the management and running of SEG Evolve. So over to Mr. Forrest.
Thank you, Alan. As Alan pointed out, this is part 2 of the DHI interpretation lecture series. We're going to talk about AVO interpretation best practices. I call it an overview. You can see on the bottom there, I put some how many years I've been involved with bright spots, less with AVO, but still 20 years, several hundred prospects. Some of these early slides are the same as were presented 2 weeks ago, about 3 or 4 slides, with some modifications. You remember the DHI, direct hydrocarbon indicator. It's an observation on seismic which indicates the presence of an oil and gas pay accumulation. Now, on probability basis, I added that. We always talk about probability. What's the probability of finding oil and gas? Geological success. And then, of course, AI, acoustic impedance, which is the velocity times the density. And bright spot, we talked about that 2 weeks ago. Bright spot occurs in usually in high quality sands, like 25 to 30%. And then we got the AVO, sometimes we call it AVA studies for the angle. In fact, the theory is really based on angle. So those 2 words are switchable, AVO, AVA. So acoustic impedance, you see that little diagram there that says bright spot, polarity, and dim spot. In the AVO world, we're going to cover all that today. Last time, we only covered the top line there, the bright spot. You can see we have a shale curve, and a water sand, and a hydrocarbon sand, which could be oil or gas. Gas is the theory, but you know, oil always has GOR, gas-oil ratio. So you have to, and remember, we have to understand the phase, polarity. So the bright spot, you remember, is softer than the hydrocarbon sand, is softer than the shale and the down dip wet sand. And then we get more complicated as we go deeper when the rocks get tighter, like 20% porosity plus or minus. So the hydrocarbon sand is softer than the overlying shale, but the wet sand is then harder than the overlying shale. And then we get in the bottom there, there's a tighter rocks again, this is depth, compaction. Effects, oops, porosity is misspelled. I didn't catch that one. 10 to 15% porosity. And the wet sand is hard with the hydrocarbon sand and essentially near 0. So those can be actually dim spots, and I'll show that in a minute. So this presentation, AVO will cover all of those categories, The world is more complex. We have VP, compressional velocity, shear velocity, and acoustic impedance. So that little diagram there, VPVS, and I'll tell you about what that is in a few minutes. We'll go through all that, and AI, acoustic impedance. So you get, compaction. As the sediments are laid down, they compact, and the AI increases, the acoustic impedance increases, and the VPVS decreases. Now note those oil and gas trends, brine, oil, and water. So when you get oil, gas or oil, you get a decrease in the AI, acoustic impedance, and a decrease in the VPVS. So you get low AI, acoustic, and low VPVS ratio. Note they overlap. That's an issue. Sometimes brine and oil look almost the same on seismic, and sometimes we can't tell in fact, often we can't tell the difference between gas and oil. Notice as you get higher AI, higher acoustic impedance, the curves get tighter together. Therefore, the resolution is much more difficult with depth and with tighter rock. This slide is a preview. It's AVO terminology and angle gathers. You hear a lot of these definitions, class 1 to 4, and I'll go over in detail what they mean. You see that little graph on the left, you'll see that several times with the 1, 2, 3. It's all about the gathers. We work in the seismic gather world. Prestack data is often the term used for seismic gather world. If you look at the bottom, class 3 or 4, those are amplitudes that are really bright spots. You see they're very strong amplitude on the near traces as well as the far traces. Now the class 3 could be a flat AVO or could slightly increase in amplitude. Class 4, the amplitude offset may go down a little bit, may decrease, but those are strong events. Then you go to class 2, and that's where the AVO world becomes very important. You see you have virtually no amplitude on the near traces, and then you have far amplitude, you have a strong event. That's called class 2. And you got class 2P, where it reverses the near trace. This is with hydrocarbons now. Remember, these gathers are with hydrocarbons. And the near trace is a peak, and the far trace is a hard, and the far trace is a soft. So you can see under certain situations, they will cancel each other, and there'll be a dim spot. So you will hear these AVO 1, 2, 3, class 1, class 2, and 3 and 4 constantly when you do AVO studies. Class 1 is very difficult. We're not going to talk about that today. It's the rocks are tighter, and it's very difficult to separate oil, water, and gas.
If I can make a suggestion to Mr. Forrest there, if you use your cursor, perhaps, is it live?
Yeah, I was going to use that. I failed to
Yeah, there you go. As you point, maybe point as you talked about.
Yeah, thank you. I should have done that. Okay, so then you remember I stressed this last time, geology first, during and after. That's one of the weaknesses of DHI interpretation, is that there's not enough geology input. And so first, during, and after. And you know how we do this, when we evaluate prospects, we do the regional geology, we read papers, geology papers about literature search. We draw regional structure maps. We make leads, map leads, understand the well ties, make detailed structure maps, and then we estimate the hydrocarbon resource variance, or volume, we call it sometimes, but reserves is a better word, based only on the geology. And we go through the 5 risk factors. Now, all of our teams, evolved teams, did this during the last several months. And you end up with a geology P sub G, which is the probability of a geologic success. It doesn't have to be economic, it's a geologic success. So then we follow up with the AVO interpretation. But we start with the basics again. It's amplitude over background. You have to have an amplitude anomaly that at some scale. And you have down dip conformance. Remember, that's to a structural contour on a depth map. That would be either an oil-water contact or a gas-water contact. Phase, polarity, flat spots, that means the sand is thick enough you can see the top and the bottom. Consistency, uniqueness, those are 2 characteristics that we talk about. And then you got the AVO and the AVO attributes, which is what we're going to talk about today. Now we're going to go into a little bit of theory here. I'm just going to touch, this is a big topic. And so I'm just going to touch on it a little bit and discuss the four papers there at the top in bold print. Ostrander, a guy named W.J. Ostrander with Chevron, published in '84 a paper, and I'll show you what he did. And then 𝐊𝐤𝐤𝐞 and Richards in '80, and 𝗠𝐈, and then Rutherford and Williams. Those are the papers I'm going to discuss briefly. Now, there's thousands of papers about AVO, leading edge and over EAGE. John Castagna, Milo Backus, Chris Ross, Fred Hilderman, there's many names associated who've done detailed studies with on AVO. So here's the Ostrander paper. You remember Bright Spot started actually about 1970 plus or minus. So in 1984, Ostrander published this paper in geophysics, and he brought up the term Poisson's ratio, which is compressibility of a rock. So the Poisson ratio decreases as you go, if it decreases to an underlying medium, the reflection coefficient decreases with increasing angle of incidence. So in other words, you have a stronger amplitude, negative amplitude. So a high porosity wet sand or brine filled sand is a Poisson ratio of roughly 0.4. If you go to, I'm sorry, that's a wet sand. If you go to a gas sand, it's about 0.1. So you get this is a model here, you get pretty good size change in Poisson ratio. So Ostrander said, if that happens, you're going to have a reflection coefficient of minus 0.16 for the top of the sand, and the amplitude will increase with offset, be more negative with hydrocarbons. With no gas, it would be flat. So you have separation in the AVO or the AVA between no gas and gas. So what is Poisson's ratio? It's a measure of compressibility. It's a negative of the ratio of the transverse ratio of the strain to the axial strain. You see that my little equation here, which I copied. You can see here, I got a rectangle, say that's rock. I put pressure on it and I squash it, squeeze it. So Poisson's ratio is delta, the difference in W, divided by W, divided by the difference in length, divided by length. So that's Now, Poisson's ratio can be expressed in terms of VPVS. You see VPVS down here is an equation. So often in practice, geophysicists will use VPVS ratio, which we get from the AVO studies. You can see here, there's a little graph of, this is VPS down to the X, and here's the Y. So you see that here would be the shale is going to be a higher VPS, and then the wet sand roughly 2 plus or minus. So the gas sand is going to be lower gas or the high GOR sand will be lower VPVS. Now, so how do we measure this? Well, we measure it from the seismic, we call it Prestack gathers, which have a shear component. You know, the reflectivity, you're going to have a normal incidence. Once you get angles, from the diagram I have it on the right, for angles greater than 0, there will be a compressional VP and a shear component, and a VS, so a shear velocity because of the angle effect. So you're going to have the vertical is a VP, and then you have the shear effect from the offset angle. So VS has a big impact on these AVO equations, but now I put some math on here. I'm just going to give you an overview of that. If you put gas in a sand, the P wave velocity drops dramatically with only a small amount of gas, and the S wave just increases slightly. So this is one of those papers I mentioned, 𝐊𝐤𝐤𝐞. This is a simplified equation. So the reflectivity of the angle, that's that offset angle, is the weighted sum of VPVS and the density. And basically, this is the basis for virtually all the AVO methods. Continuing on this theme, 𝐊𝐤𝐤𝐿 and 𝗠𝐈, they both simplified these Zopperitz equations. Now, the Zopperitz was a German geophysicist, and he published it was published in 1919. It's a very complex set of equations. And 𝐌𝐢𝐤𝐤 simplified it, as did 𝐶hui, as did others as well. And the bottom line is they end up, it's simplified to that equation there that says RO, which is reflectivity at a certain angle, is A, which is the intercept or the near trace, think about it that way, plus B, which is a gradient, which is a change of the amplitude and sine squared. So AI and VPBS can be estimated from seismic gatherings using this AVO equation. This is called the two-term equation, simplified from the very complicated Zopaerts equations. So another slide on theory, the Zopaerts equations, you can see here is this line here, and then, I'm sorry, down here at the bottom, it's the same as the three-term. When you simplify it, the so-called two-term, you can see when you get past 35 degrees, sometimes 40, you have separation or errors between the Zopaerts, which is considered the correct answer, and the two-term. So normally, most AVO analysis is based on the intercept and gradient using the simple two-term equation and the C-term, that last term, the curvature is dropped. As I mentioned, we normally just go out to 35 plus or minus degrees. Sometimes we push the data and go farther to 40 or 45, but you can see we have errors when you get to these high angles. So that's a brief summary of that. And Rutherford and Williams then came in 1989, and they defined these classes that I mentioned in an earlier slide, 1, 2, 3. And they said a class 1 is a high impedance sand, and that it was the gas sand is higher impedance than the surrounding shale. So you get a very large RA, RO, or intercept, or near trace reflection. Think of it that way. And class 2 is the gas sand near zero. There was zero contrast or impedance, but then it's characterized by increasing angles, amplitude with offset. And then class 3, you have a low impedance gas sand, have low impedance than the encasing shale with negative large magnitudes for RO, which is the amplitude or the intercept. So class 3 is a bright spot, is more or less a bright spot, as I mentioned earlier. So this terminology became the industry standard, and it helped geophysicists understand, improve the understanding of AVO observations on seismic data. Before that, there was a lot of emphasis on the amplitude change with offset. You have to think about the combination of the intercept and the gradient and break it up into these categories or these classes, 1, 2, and 3. So John Castagna added a class 4, as I mentioned in the earlier slide. And basically, if you got to remember that the AI, the acoustic impedance, is caused from the contrast from the overlying shale and the sand. And by the way, the overall shale can change as much as the sand can change. It's that boundary that causes the AI, acoustic impedance, or the reflectivity. So what John found out is that if the shale is higher VS or higher shear than the shear in the gas sand, you get the net answer is that the amplitude actually decreases with offset a little bit. So if I find my pointer again, where is it here? So the class 3, it can be a flat AVO, or it can increase, or class 4 has a slight decrease. Now there's a weakness here because class 4 sands, if you have a wet sand, it's also going to decrease with offset. So you have to be extremely careful to separate a class 4 water-bearing sand versus a gas sand. So that's my overview of the theory. And if people are interested in, there's a lot, it's a big subject, as I said, and you can read those papers and go into more detail. Now, for AVO interpretation, the simplest form is qualitative. You relate the observations to well ties, forward modules visually, and you use the seismic gathers on just the near and the far stacks, or in the angles. So when you go to and then you go into the AVO cross-pol analysis, the difference between the near and the far angle, that's more of a measurement, and you have more models. So and then you got advanced, which is, we're not going to talk about this today, fluid factor, lambda mu ray, lambda rho mu rho, inversion, EEI. So we're going to talk about these two 1 and 2 items here in about. I showed this earlier. I just moved it up yesterday for emphasis, but I don't think I have to repeat all the word. Just remember class 1, 2, 3, 4. Okay. Now look at this. This is as I meant, this is class 3 here. You remember class 2 where the amplitudes are 0 plus or minus on near traces and the increase, and the class 1 way up here where it's hard and it may cross over at far offsets. So you're in the gather world. Now the gathers, you can see down here, or the Prestack data for the class 3, it's soft, and the 0 offset is soft, and the stack is soft. Remember, we start looking at stack data, so it's a soft reflection. Then we go into class 2, and we have a weak near trace, and it's very soft on the far trace. And then we have the class 2P, as I mentioned earlier. You might have a hard on the near trace and a soft on the far trace, and you have the potential being a dim spot. So that's an interesting. So when we look at the stack data, and you can see you have different looking seismic amplitudes, anomalies, whether it's a class 3, 2, or 2P or 1. Remember, we're trying to separate a wet sand versus a gas sand. So, or an oil sand that has gas in it, or GOR ratio, gas oil ratio. So the class 3 here is on the left, and you can see that with the gas here, big soft event, even more soft with offset, but the wet sand is much dimmer. So you're looking for this difference as you go down dip. This may be on a structure, you go down dip off flank and the amplitude will weaken and look something like this. The class 2, which is tighter, normally a tighter rock, you get very low amplitude on the near offset and high on the far. And then if it's a wet sand, it may actually be a hard event on the near. So we want to see that difference. Polarity reversal. You can see we're going to have a potential polarity reversal going from the hydrocarbons to the wet sand. And you got class 2P or 1, where this is where I said that possible dim spot. Now, the AVO interpretation should be done on a robust statistical basis. Why? Well, let's start with the petrophysical data. This is from well data. And look at all the wide scatter of the data. There's an area up here, the brine sand, all those little dots. I'm having trouble with my pointer here, but and as you go down to the left, to the southwest, you have high impedance oil sand and low impedance oil sand. Look at all those different dots. So you remember every well log is a little bit different. You got sand variation, you got shale variation. So you have a lot of scatter in the data, even from the logs from the petrophysics. And then you go to the seismic, and we know all the issues with the seismic acquisition, with the ghosting and the multiples and the absorption and tuning and thin bed and all these issues. So the seismic has its own issues with a lot of scatter in the data. So that's why it's important that the AVO should be done on a robust statistical basis in the gather world, in the seismic gather world. There's a pitfall, critical angle, velocity effect. Refraction wave arrives before the reflection wave, is basically a simple way to say it. You see the little diagram here, the reflected wave bounces, here's the layer gets, the wave travels at a higher velocity here in this bed, and it's refracted up, and it arrives before the reflected wave. Here's an example that you get a very strong event at the far offset, the critical angle. It's something to worry about. We see it occasionally, and we usually just mute it out. Here's maybe a better example of the critical angle. You see at these far offsets, the big kick up here. This also is a good example of gather conditioning. The raw gathers sometimes are noisy and the gathers are not flat, and there's maybe some multiples in there. And of course, we have the critical angle effect. So you go through the series of filters or processing to really clean the data up, which is the slide there on the right, where you got rid of some of the noise and the gathers are much flatter and much smoother. And remember, when you start doing quantitative AVO analysis, you need to have flat gathers for this, so you can measure the gradient. Gather conditioning, as I mentioned, it can be very important. Here's an example. You see on the left here, you see that was the raw data, and then they conditioned it, and you can see that the events come out much cleaner. And this is a little bit fuzzy, I know that, but this is the original is the top here before the gather conditioning, and then and here's the amplitude after the conditioning, and that happens to be a pay there. That's a field right there, that amplitude. Notice we're in the gather world. Notice the amplitude changes from a soft event to virtually no event off structure. Emphasize work in the gather world as much as possible. There's another pitfall, anisotropic effects, or so-called hockey sticks. And what happens is that it's caused by the non-hyperbolic move out and corresponding errors in the attribute extraction. And you can see some examples here with the far offset, how the hockey stick of that effect, and then you have to correct it, and you flatten those gathers. And so this would be the raw data, and this would be the kind of corrected data here. There's another issue with this, when quantitative AVO analysis, you got to be concerned about the gradient. Remember, a lot of it's based on the gradient, which is that change in amplitude of offset. If the gathers are not flat, you get some errors. For example, on A over here, you can see the gathers are flat, and you get a nice gradient here, and then the gathers are not flat, and the gradient is wrong, it's in error. So the flat gathers are critical for detailed quantitative AVO analysis. Now, tuning. Seismic tuning is everywhere on seismic. Remember, we have bed thickness changes, thin beds, thick beds, and so tuning is everywhere. And you remember, it's related to the, say, velocity and the isocron thickness. And so you see at tuning thickness, you get reinforcement from the event, reflection from the top of the interval and the bottom of the interval, and you get a slightly higher amplitude. As you go further out in the tuning curve, you start seeing the top and the bottom. This is the top and the bottom here. This is separate, whereas below tuning, it's all meshed together here. And so in these, you remember in the real world, stratigraphy, sand presence, sand thickness, shale thicknesses, it changes over short distances. You have tuning thicknesses tuning issues occur everywhere. And sometimes it can be even larger than what the amplitude you're looking for is, especially for, say, a class 2 or a class 2P. Then we have a special kind of tuning called AVO tuning. That's where the normal move out in Prestack, the wavelet stretch, and also the frequency drop, a loss with offset. And the result of that, you happen to, there might be a frequency at the mid gather where it tunes properly and you get a stronger amplitude. And I've seen prospects where we have AVO tuning that looks like a gas or oil accumulation. A critical part of an AVO interpretation is the data displays. There's synthetics, you got to make synthetics, you look at amplitude versus offset, background panels. And then you go into the angle world. We're going to talk about a lot of these in the next few minutes here. First of all, you make synthetics, and you can use Gassman's equation, and you can substitute gas. If you have a well that's that's water bearing, you can substitute gas or oil, and you can get a different response. So you want to tie the wells, and you want to use Gassman's equation to do this gas, oil, and water models. You also look at it from the AVO standpoint. Here is a VP, density, VS, and AI of an oil sand. That's the top there, and you can see. Let's start at the bottom. Here's the brine sand. You can see the amplitude decreases with offset. This is angle here. You can reflectivity and angle. So the amplitude decreases with offset on the top of the sand. This is the bottom of the sand up here. You put the oil in it and it's flat to even increases with offset. So you can do all these studies, models, and you need a sonic dipole law, which is shear and density. And distance, for example, you want like to have a well right near a prospect. Sometimes you don't. Sometimes you're many miles away and you have to just do a rough estimate of what the rocks may look like or the synthetic might look like. You want to do it in the same stratigraphic interval. You want to have multiple wells. I've had prospects where you got 3 or 4 wells, you think you got a right model, and you drill your prospect, and it turns out it's a different stratigraphic section. And it's a dry hole sometimes. The logs have to be edited. Remember the log measure, the logs over near the borehole and the seismic over an area. So there's a lot of issues that you need to consider when you do these models. So pre-stack data, you look at the gathers. Now on the left here is the offset stacks. You see, again, you hear this often, near stack, mid stack, far stack. That's common terminology. You're just measuring the amplitude change from the with offset. And of course, angles is a theory, and you can see it over here. You can calculate the angles like with the colors here. And so you have offset stacks and angle stacks. Now, the offset stacks is fairly easy to do. You have it like, let me give you a couple of examples. Here's a near offset stack. You see these amplitudes here, and you did the far offset, and the amplitude increases. It blooms a little bit, blooms. And by the way, it's just also a sharper down dip edge here for down dip conformance. You can also do it with angles. Like this is a near the 15, and this is the far angle. That's that. And generally, you're looking for a higher amplitude with offset. Here's an example from the North Sea. This is probably better. This is a class 2 anomaly I happen to know. I've looked at it in the last few years. And there's a structural high here, the simple closure. Pardon me. There's a simple closure and about maybe 200 or 300 feet. And this is the near stack, and here's the far stack. Look how this amplitude blooms on the far stack there. It's an AVO, and this is 100 million. This is 100 feet of oil, by the way, and it's a 100 million barrel oil field. So that's a great example of the near stack versus the far stack. I always like to bring in amplitude versus background because remember it's the #1 characteristics in it for DHI interpretation, and I showed this in the first talk. But in some cases, the near and the far offset can have a different polarity. You might have a soft on the near and a hard on the near and a soft on the far, and that would help you identify down dip conformance and map down dip conformance better. So always think about this amplitude over background and down dip conformance while you're doing these AVO studies. You have to incorporate geology into the AVO interpretation. This is a weakness, I feel, in many of AVO prospects with AVO, I should say. It needs a geological model or models. And sometimes the geophysicists, they get focused in on one model and they drill the well and find out it's something different. So you need to look at several models when you look at this AVO, what's causing the amplitude and what's causing the change with offset. So integration of the seismic and geology should be done by the interpreter, the geologist, and the AVO and or the data processor. And you have to be aware of these bed thicknesses and tuning. Remember, the geophysicist sees 30 or 40 feet. I know we're doing better today in some cases, whereas the well log, and the core gets down to inches and what you can resolve. So you have to understand the geology. You have to understand whether you're in a Pleistocene or my age sometimes, but mainly geometry. Sometimes you have a sheet sand versus a elliptical sand. And that will, where you have a sharp top or a hard top, and that can impact the amplitude and depositional environment. Whether you're fluvial or alluvial or delta mouth bar or offshore bars or deep water turbidite or channel level, levee. This all should be incorporated into your geologic model when you do your AVO studies. So a good approach is to model, as I mentioned earlier, to model all these feasible, scenarios, analyze each of them. Some people like the words confirmation bias. In other words, test alternate hypotheses that may be different from your favorite hypothesis. You got to be worried about pitfalls, which basically are dry holes. Wet sand, we talked about that in the first talk, higher porosity than expected, hard shale or oil. Low saturation gas is still, remember, it's a issue with bright spots, same with low saturation gas. Gas in a non-permeable rock. I've seen prospects where they had gas in a silty shale, or just a silt, it was non-permeable, and looked like beautiful AVO, would not produce oil and gas. No nearby calibration, bed thickness issues, AVO tuning that I mentioned earlier. So there's a lot of reasons to go wrong. And I'm going to show you here some examples. This is a qualitative interpretation. There's a fault, there's an upthrown fault trap here. Here's the fault, here's the map, structural closure. You notice those letters, A, B, C, D, E, F, and you can see that here's, remember, in the seismic gather world, so there's virtually no amplitude over to C, and then D, E, and F have a strong amplitude, and also it looks like slight increase with offset. So D, E, and F, so that would be an AVO anomaly on a qualitative basis. Now, notice the gathers are not flat. That's okay for qualitative analysis like this. The gathers need to be flat when you start measuring the gradients and doing more quantitative analysis. Here's another one. This is in the North Sea. There's McCullough. Actually, this is in the same field that I mentioned earlier, McCullough Field. There's a closure here, 100 million barrel field. You can see that this is the event here. This is AVO class 2. We have very weak anomaly, weak amplitude on the near, and then softer on the far. Now there's a weakness here. I like to see these gathers to go much farther off structure. You want to see the difference in the amplitude in the gather world between your prospect and the offset, whether it's a wet sand or maybe it's just no sand off structure, and you want to even to tie wells in the seismic gather world. So I'm emphasizing the gather world is critical, seismic gather world. We often show, this is the same field, by the way. This is, remember I mentioned Poisson Ratio or VPVS. And this is a plot of Poisson Ratio versus AI, Acoustic Impedance. So on top here, these are the shales and the wet sands, and then you put the hydrocarbons in there, and you got low impedance and low VPS ratio. This is a pretty spectacular one. That's 112 feet of oil there. It worked here. I can tell you there is a nearby prospect here that didn't that people drilled years ago. It didn't look this good, and it ended up being a dry hole. So you have to do a lot of detailed studies. Here's another example. This is the gas condensate discovery in the Norwegian Sea. It's Middle Jurassic, and you can see here it looks like it's a fault closure here, unconformity, and the near track stack, the 5 to 15, and you go out to the Forrest stack, you get much higher amplitude. You can see that with that on the right there. I'd call this probably an AVO class 2 and 3. I should have mentioned this earlier. We say AVO class 2 and 3, but sometimes there's 2-3. Those curves, you can have something in the middle there, or even 1-2. Here's another example. This is over in Australia. You can see that now there's a structure here. It doesn't really show up. This is a high here. You can't really see it here. But this company, Woodside, by the way, they took the near angle. They took every 5 degrees all the way up to 50 degrees. And so you can see on these near angles, there's virtually no amplitude response at all. And when they get to the far angles, very far angles, you see this, a bright amplitude. Well, this is a channel sand here. By the way, it has gas in it. It's successful. a channel sand that crosses this high, is a channel sand right here, and you have to have the very far offsets to find it, to identify it. So one of the major points that I'm trying to cover here today, I'm trying to say, you have to understand the Prestack data technology, and you have to understand the 4 AVO classes and what they mean. You have to make synthetics. You have to tie the wells, and you have to you have to remember the well logs have uncertainties similar to the seismic. We have data quality problems. Use a robust statistical technique for balancing the amplitudes. Look at a lot of data. Sometimes we see prospects where a geophysicist shows one gather on the crest and one gather off structure. That's not good enough. You need to look at a lot of, that's why I like these gather panels, as I mentioned earlier. Seismic data quality, you have to worry about all the processing and acquisition and normal move out, the phase, et cetera, and the AVO tuning. And the gather can be made a better quality with gather conditioning. The gather panel, this is my favorite subject. I love these panels. They're very useful to review a large amount of seismic data and to show data on and off the prospect, way off the prospect, to observe changes from the AVO anomaly to either a wet sand or maybe it's a no sand. A prospect with an AVO anomaly should have a geological model. I should emphasize that earlier, and you should do a feasibility study based on a thorough understanding of local geology. And be aware of the overlap, as I mentioned in one of those earlier slides, the water and oil overlap. Sometimes gas and oil and water all overlap if you get into a class 2P, for example. It could be very difficult. Pitfalls, no calibration, of course, wet sand, no saturation gas, gas in a non-permeable sill, as I mentioned. AVO. There are other pitfalls, as I mentioned in an earlier slide. You need to have the interpreter and the processor work together to understand the acquisition and the processing to get really the best AVO interpretation. And interpreters should be aware of the geology, seismic, calibration uncertainties before and during and after the DHI interpretation. There's more uncertainty sometimes than what we realize. This process is a lot of it's modeling, and you tie the models to from well data, and you tie the models to the seismic data, and you do the gathers and the angles and the offsets, and then you can do cross plots. But everything must be integrated with the geology to be successful. So this is kind of a summary here. A DHI prospect requires several strong amplitude anomaly characteristics. AVO is one of those. Remember I said the number one is always down dip conformance on a structure map. AVO is normally not a good prospect. If you just have AVO and don't have any other characteristics to speak of, the risk is high, very high. So AVO analysis is a very good additional tool to evaluate DHI prospects, but it's not a panacea. In other words, it doesn't work all the time for gas and oil exploration. So I hope I didn't go too fast. We're gonna pause here for comments. And I have another part here, addendum or intercept gradient discussion, which will take another 10 or 15 minutes. And so let me move forward though and just show this at the end here, and I'll come back. You remember I showed this in the first bright spot talk, is that amplitude anomalies, which an AVO is in that category. If you have a DHI support, this is Exxon report of 500 prospects. They went in with 55% probability of technical success, and they actually got 70%. I consider a good DHI prospect a 70%, 75%, but you have to have those multiple characteristics. But on a pure geologic prospect, tidal rock, carbonates or something, you can see the average is about 35%. So you get about a factor of 2. That's technical, or we call it geologic success. Some people call it technical success, but the economic success is less. especially in deep water, and you have to have larger volumes to be economic. Alan mentioned this earlier. I like to start on the bottom left here. It's about curiosity and creativity, resilience, tenacity, staying power, never give up. Of course, the software is involved, 10 or 20, maybe 20%. Some people think it may be larger, but your numbers may be different than these are our numbers. Over time, you might argue with neural networks, machine learning, and all this, that this may go up somewhat, increase. But the big half of it here is this experience and knowledge and thinking, and we call it critical thinking. And in the business, you got everything has to tie to the business model. That sometimes if people find big, especially gas fields, and they end up being, say, stranded gas because they can't get a pipeline to it. So you have to think about the business side and the economic side as well. So let me go back to that. We're going to pause here for a few minutes and give the group a chance to make comments or ask questions. And the second part, addendum, is more quantitative, which is intercept versus gradient. I don't think I'll have time to cover that before 9 o'clock. So Alan, why don't you take over here for a few minutes?
Sure. So if you unshare your screen, yeah.
Okay.
So first of all, I think we would like everybody to give you a digital round of applause here.
I hope I didn't go too fast. I hope it wasn't, all of our students have not used AVO data. They haven't used Prestack data in their database studies. So this may be new for a lot of the students.
And maybe I'll add a few of my own comments, in part based on my own experience. They may overlap significantly, or they will overlap with what you say, but I'll kind of give my own experience and trying to think of these students, because they saw, for example, a lot of equations today. So, there are some very complex equations in AVO. Now, for some of today's students, they probably do the Zoprist equations from first principles on weekends when they're bored, but I'm not one of those, by the way. So we have some very complex equations. Honestly, I don't understand them. The second thing I'm going to say, and by the way, those of you who know me know that I tend to exaggerate to make a point, so warning. So I'm going to say there's 100 factors, as you just saw, that influence a seismic signal. One is hydrocarbons, the other 99 or something else.
Especially the wavelet. The seismic wavelet is a big factor.
So yeah, so I'm just making this point that anybody that thinks AVO is something really simple, so you got one piece of the signal that has to do with what you're looking for, and potentially up to 99 different factors that could be present. So this is in many ways an overwhelming challenge in the real world. So what I say is, what's a poor interpreter like me to do? I mean, I'm not very good at math, and I don't know all the seismic noises. So we're going back to Mr. Forrest's talk. So what I do, I focus on the qualitative. You mentioned qualitative.
Right.
I focus on the visual. I may not know the equations, but some of the displays that Mr. Forrest showed, I knew right off the bat which ones made sense and which ones did not. So we're back to be visual. Understand as best you can the theory, but look at the data. Visually, you'll often understand what's going on. Understand the geology. If you understand that something just doesn't make geologic sense, you don't actually have to know all the equations. And then the other thing is, of course, experience. So that's sort of what I wanted to add as kind of a perspective based on my own experience. Did you want to add anything else, Mr. Forrest, on those points?
Well, no, I think, let me go back to this Rutherford and Williams, when they published their paper back in what was it?
And then we'll try and close out after that. And then
that was a simple paper. It just set up these definitions for the 3 AVO classes. But John Castagna, he's friends of us, and he tells us that was a critical paper because it put the data in categories that people could think better about certain anomalies and how they fit into geology. Before that, I think I think I didn't do much AVO at that. Wasn't doing any AVO at that time personally, but I think people were just looking for amplitude changes with offset. And you gotta think about the intercept. You gotta tie it to the geology, and you have to think about all the pitfalls. And there's been AVO has helped find some big fields, but it has also led to a lot of dry holes. I can just tell you that there's many. In fact, over in the UK and Europe, in the North Sea, the UK Oil and Gas Authority, they did a study a few years ago. Why are so many of these wells dry holes? And then a lot of it, they said, well, they were over optimistic. A lot of it is also people, geophysicists, geologists, we get over optimistic. We want to find oil and gas, and we try to make it look better sometimes than what it really is. So, and you have to have peer group reviews. You need people. You need and you need experts. Interpretation is what I do, but you need somebody who knows all that theory, and you need somebody to work with who understands the prospect, geology, and you have to integrate all this information into one final interpretation. So the Rutherford and Williams categorized the 1, 2, 3 end up being a big. And by the way, Steve Rutherford, he came to a meeting I was at. This is a funny story about 15 years ago. Tenneco, he was with Tenneco. And Tenneco was getting ready to sell the company. And Rutherford and Williams had written this paper, and they were going to publish it. And they went to management and said, go ahead and publish it. We're going to sell the company anyway. And so they, at the last minute, they decided to call it AVO 1, 2, and 3. That was a last minute decision. And so Steve Rutherford came to a meeting. He said, we're still astounded that classifications, they originally had just high impedance and low impedance, those kind of words. And then the last second they put on 1, 2, 3. So, but anyway, that's an interesting story. Go ahead, Alan.
Okay, so yeah, since we appreciate everybody's time, we're going to do a mini closeout, those of you that have 10 o'clock meetings, but stay around for questions. So as I said,
we're going to do intercept versus gradient. That's I think about another 10 or 15 minutes.
So I'll just do a quick few closing comments. And again, those of you who want to stay for the Q&A for the previous talk on bright spots, you can ask questions about that and this one. So are we seeing the right screen here?
Right. Yeah, you see Rocky.
Yeah, very good. So just quick update here. So next week, we have Mr. Rocky Roden giving us a talk on what geoscientists should know about machine learning. Both Mr. Forrest and I know him very well. He's been in the industry a long time, expert in all these AVO as well as machine learning. We're working on other topics, so we don't have the exact dates, but we expect something on the petroleum geology of the Niger Delta. One discussion I'm having with Dr. John Carlo, who talked to us before, he wants to give a talk on how he can look at your maps and know immediately that your map is wrong. So we're sort of working on that, also working on something on source rocks. So we'll keep you posted on that, go to our channels, etc. Just a quick promotion, this program, of course, there's some costs associated with the program, including in good years, we fly the key students to the annual meeting. So if you're an oil company, you can come here to this link, sponsor a team. You can sponsor one team or you can sponsor more than one team. We would love to have you do that. If you're an individual, you can come to the SEG site. You can get there from here. Minimum $10 contribution. Feel free to contribute 10 bucks so we can keep training the explorers of the future. So we're going to close out here with one of my favorite pictures, Nate Schlegel, one of our volunteers who is unstoppable. And so SEG Evolve, the students, we are not afraid of the future. We are the future. So for those of you who are leaving, we will see you next time. And for the rest of you, hold tight, and we're going to go to the Q&A. Thank you very much.
Okay, can I share again now?
Well, let's hold off for a moment and check with our producers here. Yeah, we got to make sure everything is okay.
Check with your high-tech people.
Yeah. So Mario, are we good to proceed to the Q&A? Oh, so hold on.
Yes. Yes. Sorry. asking questions. We have some questions already in the chat for you.
Before we begin the lecture or the additional slides, let's have a quick look in the chat. I want to see, and then are you going to keep feeding the chats?
Yes, sir.
Okay, so I see one question here so far in the Zoom chat. Is that what it is, or are there more?
Yes, go with that one.
Okay, well, I think maybe this is worth addressing. So are there any further comments on how to identify and account for anisotropy?
Oh, that's difficult. And also, those anisotropic effects are, you know, there's a theory behind it, which is correct, by Leon Thompson. Leon Thompson did a paper about 25 years ago on the anisotropic effects. It's very difficult. I don't know of any positive way to identify it, but it can cause a false AVO anomaly. I didn't show that in this talk, but you can have and sometimes people, when they have an AVO prospect, an anomaly, have an increase with offset, and it's a wet sand or something, and they speculate that it may be caused by some kind of anisotropic effects, but it's hard to prove. It's very difficult to prove.
Okay, so let's see. We have another question here. In modern processing, which technologies are the most AVO friendly? And these guys have tough questions for us.
Oh my gosh. Well, AVO friendly. Well, first of all, you have to be careful with the far offsets. You know, the far offsets, sometimes you actually mute them out because of the data. You get these hockey stick effects, or you get or you get a possible critical angle. But for quantitative analysis, you have to have flat gatherers. I know there's, you know, velocity is critical. Now you got this full wave imaging. FWI has come along in the last few years. That's you know, modeling. It's velocity modeling. You can get a much higher estimate of your actual velocity, and you have fatter gathers. It just takes a dedicated effort, and I think, as I tried to stress, you have to have the geophysicist who's mapping interpreter and the AVO processor working together as an overall team. That's the most critical part of it.
I guess I'll add a perspective on that because, you know, we could talk about many AVO friendly procedures, and the contractors will talk about those. Again, I would say, just as an interpreter who is neither an expert on mathematics or processing, I try to be aware of at least what is very AVO unfriendly. And I'll give you an example. I worked on a project in Mexico where all the near traces, because of acquisition, had been, you know, reduced amplitude. So they were seeing AVO all over the place. They, you know, there wasn't recognition initially. It was just bad data on the near traces. So be at least aware of the obvious AVO unfriendly. That's probably a few things. And then back to what I always do is I do my geologic checks. If I see a certain response at my target, I go up and I look at a horizon above and see what that's doing. And so if I have a big AVO and then there are two horizons above that are in a shale package that also show AVO, there's probably something wrong. So once again, you know, technology itself is not going to answer your questions. It's not going to find the oil. You got to use your geologic thinking.
Well, plus the model. If you want to tie it, if you have nearby well data, you have these models using Gassman's equation. You want to see if you can tie your seismic data to the model. I'm going to show that next when we get to it on the intercept and gradient cross plots. But,
okay, so actually we have one of the students on Zoom who wants to ask the question on microphone. So maybe it's a tough one. So
go ahead,
Mr. Sohail, go ahead.
Go ahead.
Hello, everyone. Thank you so much, Mr. Mike Forrest, for delivering a wonderful talk again.
Hope I wasn't too fast. Okay, go ahead.
All right, so just a quick question, a bit far from the topic, but not really, it's kind of interrelated. So I wanted to know your opinion on integrating AVO with inversion and its interpretation.
Inversion, yeah, I didn't get into inversion. That's a separate subject. Inversion is another step in the, say, quantitative. They call it QI. You probably hear that term a lot, quantitative interpretation. That's when you take the AVO attributes and you try to actually to estimate rock properties like porosity and water saturation, etc. Inversion. Inversion is a general term. You got to be careful when you use that word. There is say post-stack inversion. There's say pre-stack inversion. There's colored inversion, whatever they call it. There's many different kinds of inversion. So inversion, you're just trying to change the seismic response reflectivity into layers. So it looks like a log in a section. You know, it's representative of a log. That's all you're doing, and it's a specialty in itself. You have to have experts, and you have to have nearby well data to really calibrate. It works well if you're in a field, if you have found hydrocarbons and you're drilling the second or third well, and you know, we have calibration to help you. Then you do all that high tech stuff. Inversion can be used for, you know, for exploration as well, but it's not as reliable because usually the well data is sparser and farther away. But that's a special topic.
Thank you so much, Mike. Thank you.
Okay, and I think we have, let's see, who else?
I have one more.
Mr. Uzono wanted to ask a question on Mike, so go ahead.
Yeah, so thank you, Mr. Forrest, for the wonderful presentation. And yeah, so we normally interpret seismic on full stack gather. And then, you know, like the exploration work we have just completed on Evolve.
Right.
We don't have any angle stacks.
Right.
How do you try to carry along what we have heard from you with regards to trying to, you know, notice or pinpoint AVO variations, you know, while interpreting full stack gather without having any access to the near stack or the fast stack gather?
Well, we're using public data sets that Alan has, and they're all just, a lot of these data sets are old, and we don't have access to the so-called pre-stack data or the gathers. But Alan is working on that to get an AVO data set for the future. Yeah, so your project the last 6 months was really tied to my first talk 2 weeks ago, where you have to just use the stack data to analyze down dip conformance and amplitude over background, et cetera, that I mentioned, consistency. You need those gathers, you need the pre-stack data, as we call it, and Alan may want to comment on this. He's trying to get a database with pre-stack data.
Yeah, so I will make one point, and you know, having been a former leading edge editorial member, words are very important. So Mr. Uzono, you mentioned full stack gather. That's a little bit contradictory, actually. You're referring to, you interpreted on full stack. Gather is the pre-stack.
Yes, sorry.
And I don't mean to be picky, but
full stack volume.
There we go. Yeah, and remember, when you make like a prospect presentation or something, believe me, everyone looks for every little flaw. One word could be enough. So I'm not picking on you. Just a learning experience. So that's
thank you so much.
Yeah. So what I would say is that, you know, in Evolve, we did indeed give you stacked data. So as Mr. Forrest said, we're just working on really what he was showing last week. You can find the bright spots. Now, in terms of if you're in a real world oil company, what I might do is some modeling based on the wells to see whether I would even expect an AVO response. Because in an oil company, if you want the pre-stack data, you're probably going to have to pay the seismic contractor. So that's what I might do in the real world first. And then if that's the case, I would then pay that contractor. As far as Evolve specifically, you know, we do have some pre-stack data in some areas. You're welcome to apply to come back again next year. And let's see, we'll try and get you a pre-stack data set next year. But, you know, just a quick philosophical point, by the way, Mr. Forrest and I often say, look, we want you to understand the basics first. You know, we want to make sure you understand the geology and the faults and the fault polygons and how to do contours and what makes sense geologically. So it's fine to work on the stack in detail. Once you have that under control, the pre-stack domain is next. And yeah, as I say, we're working towards always adding those. So next year we'll have more.
Yeah, sometimes it's good that the AVO data comes afterwards. Sometimes geophysicists get so excited. It's an interesting subject. And they get so excited about the AVO that they're rushing to the prospect and they forget those basics of geology and the basic bright spot interpretation. And so sometimes you're probably well off not doing in the AVO studies until the next step, because you have to understand the prospect geology and interpretation on this say stat data before you go into the AVO world. That's my view anyway.
Okay, I have a second question, please.
Go ahead.
Yeah. Okay. So, assuming you have, if you have a near stack volume and a far stack volume, and you said in your presentation that is actually best, right, to do AVO on pre-stack gathers, but now you have a
pre-stack data. Okay. Go ahead.
Yeah, you have a post-stack volume of near and far. What can you do with that with regards to AVO?
Well, you can do a lot. That would be, say, qualitative. That's what we call qualitative.
Okay.
Remember I had that one slide where the gathers were not even flat and there was an upthrown fault trap. And no, you can do a lot with just the raw gathers, near stack, mid stack, and far. It's common to make three near, mid, and far. And if you tie it to the geology, if you tie it to your prospect and your structure and everything, you can do a lot there. You can do a lot there. In fact, that's really step one. That's what you should do before you go into all this angles and all this intercept versus gradient, which I'll talk about next, and all this inversion, as you mentioned. You should just look at the regular stat data. That's a good starting point.
And I'll second that point, because again, I like to come from the geology, which is I like to work my full stack really hard, understand the basic geology as well as I can. Then actually I don't go to the gathers. The next thing is I do look at those partial stacks. And by the way, sometimes you might look at the three and conclude, you know what, my near is actually bad, like the case I described. So at that point, I actually have to do in the workstation far minus mid. Sorry, that's the best I can do because I can't trust the near. But to me, that's the sequence. You work your full stack, you understand it fully with a very strong geologic emphasis. You go to your partial stacks using that same approach. Then you go to the gathers that have the lowest signal to noise. These others have higher signal to noise. This is now your lowest signal to noise with the most potential for the other 99 pitfalls. So that's the way I personally do it.
And that's part of this critical thinking, by the way. What Alan just described was critical thinking. You start with the easy steps and then make it more difficult as you go along.
Awesome. Thank you so much.
Let's see. I see we're good in terms of questions on the Zoom. Mario or Jesus, are there any other questions coming in from the other venues? Or
we are good on questions right now, so if Mr. Forrest wants to go ahead and give his second part, that'll be great.
So you can share again. Yeah.
Okay. Do you see me? You got me up to, do you see it?
Yes, perfect. Thank you.
Okay, so the intercept and gradient. You remember I said that equation, the amplitude and the angle is the intercept plus the gradient times sine squared. Well, you can take the background. This 45-degree line here is the background. That would be the wet sands and the shales, and then you can make a cross plot of the intercept, which is the x-axis, and the gradient, which is the y-axis. And you can start identifying separation from I like the word separation. You separate from this background. This is the wet sand here, and you find there's an anomaly here. Now it won't be a dot; it will be points all over the place. And you say, oh, well, that's a class 3 anomaly. There's separation from the background. Or you can go with class 2. You remember that has a very low amplitude on the near offset, and on the class 2P, and here's the class 4. And so you can, it's the best way to, the best way to think about it is this. We talked about the amplitude, the reflection versus angle. So this would be the wet sand, this would be an oil sand, this is a model here, this would be a gas sand. And all I do when I put this in the intercept gradient cross plot, it just shows it in a different format. Here would be the wet sand, that's that background line, that 45-degree angle line. And this would be the oil sand, and this would be a wet sand, this would be a gas sand. All you're doing is just putting it in the data in a different format. And so you can see here that, this is another way of looking at it, that it was a class 3, class 2, you see those gathers there. And so here's the back, so you're looking for separation from this background line. Now, the background line is not a constant. The background line is another complication. That's a slope of the background line, can be variable related to the VPS ratio of those sands and shales. So you got to remember that it's never exactly perfect, but that separation, you're still looking for that separation of the possible hydrocarbon bearing sand and the background trend. For example, this is the intercept gradient, so this would be the intercept and the gradient. So this would be the background here. This is a perfect case. There's no noise. The points are all lining up together, and this would be the hydrocarbon effect. So here's that separation. So here would be the class 3, this would be the 4, this would be the class 2. And you can see by the time you get down to class 1, you get very little separation. Now excuse me, the real data looks like this. So because of the scatter and not only the petrophysical, but in the seismic data. So here's an example where a critical, and by the way, you calculate intercept and gradient volumes and you make a cross plot. For example, here's the background, and here's the anomaly over here. This is the top of the sand, here's the base of sand. It's good practice when you get an anomaly to post it on your seismic line. In other words, this anomaly was right there. And you say, oh, look, I'm on the crest of a low relief feature, a low relief structure, and also the amplitude is brighter there. So it's all making sense. So post that amplitude, that AVO anomaly from the intercept gradient onto your seismic data. Condition gathers sometimes can make a difference. Remember, I mentioned that earlier in the talk. This is the seismic line here. This is the raw data, and here's the intercept. This is the background. This would be the top sand, base sand, hydrocarbons, and then you do this, tuning up of the data, condition data. First of all, you see the data itself is much better. You see those amplitudes down there on the seismic section. You can see it's a lot sharper. It's a lot sharper here. Anomaly that looks like a class 2-3 down here, and this is the top and that's the base. So sometimes you have to mute the far gathers. For example, this is a seismic gather. Look at the data here, and so if you did the non-muted case, you said, well, where's my prospect? Where's my anomaly? So common sense, you get rid of the data that doesn't look right. That looks like it's, you see there's kind of a vertical effect here. So you mute that, and then you get in a good AVO anomaly. This is the background again. This is all that's wet sand and shale, all this rock that you don't care about. You care about this right here. That's the anomaly. Notice it's not a point. It's a wide scatter of data. Now phase, remember I talked about phase in the first lecture. You want to have a 0 phase wavelet, if hopefully, or close to it. And so you can see that this was the original one I showed. You muted them and there's the anomaly, but look at the difference when you change the phase. So it looks like this data is out of phase. It looks like your best anomaly may be 90 degrees, almost 90 degrees here. You see, here's the top and here's the bottom of the AVO anomaly. you have to remember all the time this overlap problem. As I mentioned earlier, the brine sands and oils, the shale and the oil. I didn't put gas on here. Gas would be further to the southwest there. So this overlap not only on the intercept gradient and on amplitude over background, you're always going to have that issue. So here's an example in the North Sea that I know about. This is a Dunbar. This is a low relief closure here. It's the closure has a little southern lobe on it. See this down to the south here. And this is an AVO class 2 anomaly. And you can see here's the background, and here's the base, the top sand, here's the base sand, and they plotted it on the section. And at the time, this particular company had an oil field here. That's to the north here. And they did this AVO analysis, AVO studies, and they plotted it on a cross section, and they said, oh, it looks like we have a little nose down, we have a south plunging nose, low relief. And there's another prospect down here, which by the way was missed by the company in their first phase, exploration drilling, production drilling. Anyway, they drilled this well and found 58 feet of oil. So this was a good drilling result from the intercept versus gradient cross plot. So the intercept gradient cross, I consider it a powerful tool, and it should be done on every prospect. And if you have forward models, if you have nearby well data, you can plot the well data on there as well. For example, we don't have it here, but you can actually plot. You can plot some wells on here and just see how it matches. And you want to be aware of the overlap, as I keep mentioning. Now, there's also, more advanced processing, as I mentioned, this lambda rho, mu rho, and then extended elastic impedance. That's an extension of the intercept gradient technology. If the prospect warrants more advanced studies. This is a step-by-step process. I like your question a while ago that said, what if I only have the near stack and the mid and far stack? That's a good starting point. You work your way along step by step, and then you go to the angles, and then you go to the intercept versus gradient. And in some cases, I've seen prospects recently where I see this EEI technology, where it's the same base. You're just trying to get separation from a background trend. So I think I showed that earlier. I think that's it, Alan. I did that faster than I expected, but that's the intercept gradient, which is think of it this way. It's a simple way of thinking about it. Okay, Alan.
Okay, I'd like to make sort of one other comment, in part based on my experience. In some ways, the most important slide, I would say, in my own experience, you showed is that one about just a few percent gas can change the signal as much as a totally commercial. So in other words, a non-commercial few percent of gas can give you the same seismic response as 90% hydrocarbon or 80% hydrocarbon saturation. So that's a real, that's a sobering insight, because it means you can do all this wonderful work on bright spots, you can do all this wonderful work on AVO, and you're still left with that ultimate ambiguity. My science is perfect, and yet, is it 2%? There's that chart, that red line. Am I in a case of, we'll call it 5% gas saturation or 85% gas saturation? And obviously that's the difference between a dry hole and success. And so I'm going to say, this brings me always right back to, no matter how great my AVO anomaly is or my bright spot is, I look at it 100 different ways, slight exaggeration again, but I look at all the geologic factors. I think really hard what would point towards this being commercial versus just a few percent. And guess what that brings you back to? What we call the magic 5, source. So is there a good source? Do you have a migration pathway? Clearly. Are you sure you don't see any little cracks above the top of the salt or of the reservoir like Dr. Carlo talked about? So this slide should be very sobering for everyone, and it just tells you, you've got to go back to geology and the right side of that chart that Mr. Forrest showed.
I saw a prospect a couple of years ago, and it was a low relief feature, and it had many AVO attributes. It had an amplitude anomaly that AVO class, I guess was class 2, but it fit structure. And they had the near stacks and the far stacks and the angles, and it was in fact, we had a group of people that evaluated, called it a 70% probability of success, geologic success. But the biggest risk was reservoir, because they had indications in the area that the reservoir, well, there had no evidence of reservoir in the area, and there was because it was a new play idea in a proven basin. So the company actually, when they drilled a well, they only used a probability of 10 or 20%. They didn't use that 70%. They let the reservoir geology story override the DHI story. And so they went from it because of this problem with this low saturation gas. They drilled a well and found a gas in a silty, kind of a silt, non-permeable rock. So the point is, sometimes geology can override your DHI interpretation.
Yep. Okay, maybe you can unshare. We'll see. Let's see if anybody else on the YouTube or Facebook wants to send in any questions, which will be forwarded to us in the chat here. So kind of, we're down to our final few minutes. So last chance from YouTube and Facebook for any questions. And I guess the student teams, if you got any last minute questions, put them in the chat yourselves directly. So I think then, I'll check with my producer here, our producers. So Mario, I guess I would say that if we don't have any final questions coming in from Facebook and YouTube, I don't see anything here coming from the students. I believe we can call the event complete, if you approve.
Yes, there's no more questions going on right now.
Okay. All right. Well, again, thank you, especially those of you Facebook, YouTube. You've stayed with us for about an hour and a half. We appreciate you being with us today. Hopefully you got a flavor of how we interact with these students and the mentoring they get. And by the way, this is just 2 of the mentors today. We have a lot more highly experienced mentors up on workflows, workstations, everything. So anyway, thank you for coming. See you next time. Thank you.